Hey, welcome to the channel where I talk about deep learning papers, NLP papers. And today our topic is GAN BERT Generative Adversarial Learning for Robust Text Classification. It's a way to use semi-supervised BERT in NLP domain to gain a very high level of data efficiency. So why is this paper special? This paper introduced the semi-supervised GAN in NLP. Is one of the first papers they talk about they leverage the semi-supervised GAN in NLP, and it fine-tuned BERT model with unlabeled data, because labeled data is very expensive, but we somehow have a lot of unlabeled data. If you can leverage that, then your BERT model will be even more powerful, and you can achieve the very reasonable performance under a very low resource environment like this. They can have the decent performance when only seeing 50 examples. If you are familiar with NLP, 50 examples are very, very little data. And this graph better illustrates their power. So basically, they compare their model GAN BERT with a standard BERT, and as you can see, if they only channel 1% of the data, then their model basically can achieve over 60% of the accuracy, while the BERT model only have 1%, only have 20% of the accuracy. Basically, it's not converged yet. And when you boost your training data to 2%, their model achieves 80% accuracy, which is very high, and the BERT still not converge. So you can see how data efficient this model is. And this paper is a joint work from University of Rome and Amazon. If you would like to receive more deep learning explaining videos like this, don't forget to subscribe. So while it's a semi-supervised GANs, it's still the structure is still a little bit similar to traditional GANs. So basically, you will still have a generator and the discriminator, and in this case, you will have the real data from your label from your training data, and it labels which class this data point belongs to. And you also have the fake data that generated by the generator, and your discriminator will need to classify if this data is real or is fake. If it's real, it also needs to classify which class it belongs to. So basically, is real or is not? Is it real? And if it's real, then which class is that? You don't have to build a hierarchical classification. You can just formalize it as a traditional classification task. If you have five different labels in your task, then you have 5 plus 1 total classes, because you have 1 plus class that's for the fake class. So if you have k classes, you have traditional k classes labels here, then you have the k plus 1 class for the fake class. And this graph illustrated this better. You have the k classes, there's a real classes, then you have the k plus 1 class, that's for fake class. Then your discriminator will just do the classification. They have k plus 1 classes. Alright, let's take a closer look to the discriminator loss function. There are two different parts of discriminator loss function. The first part is supervised term. Supervised loss term is to calculate the penalty of you classifying the real label example. So basically, you need to, if this example is real, then you need to correctly classify it to its corresponding class. So you want to maximize the log probability of given the condition X to get the corresponding class. So your class only can be 1, 2, 3, 4, blah, 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 2k. You need to classify this real example correctly. This is for label data. And another term is for unlabeled real examples. Unlabeled data, but it's real. And also for unlabeled fake data. Fake data will not have label as well. So as you can see, this term is for the real example, real unlabeled example. If you classify the real unlabeled example to K+1 class, which is a fake class, which means if this example is real, then you say it's fake, then you got penalized. So you want to minimize this probability, this kind of probability of classifying the real unlabeled data to a fake class. And second term is easier to understand. If this is a fake example, you want to correctly classify this as a fake example. So you want to maximize the log probability of this fake example of being the fake class. Because it's a loss function, so there's a minus term here, minus sign here. So you want to maximize this value, log probability, which means minimize the loss function because you times the -1. And the real loss is just combine this supervised loss term and unsupervised loss term. As for the generator, it's even more interesting. The generator takes the input because your generator wants to. The goal for generator is to generate the hidden representation that's very similar to the real hidden representation. And how we get a real hidden representation is very simple. We have one BERT model, then we have the input example, label input, and for a given input, the BERT model will generate a hidden representation for that example, and the generator basically wants to mimic that. And the generator will have 100-dimensional noise vector that is randomly generated. Then after this generated neural network, you will have the fake hidden representation of this fake data. And the loss function is trying to encourage this fake hidden representation. This is a real hidden representation. This is a fake hidden representation. It basically wants to the fake hidden representation as close as similar to the real hidden representation as possible. So we have the loss function is like this. You subtract the real one to the fake one. If they are very similar, their subtraction result will be nearly 0. Then that's when you succeed. And also, this is one turn of the generator function. And if the generator generated a fake example and is detected by the discriminator, it will also be penalized. Like this example, if the generator generated one example as a fake example, and the discriminator successfully classify this fake example as a fake class, then your loss function will be written like this. You don't want this to happen, so you want to minimize this the probability of fake example being detected by the discriminator, because you want to minimize that. So in the loss function, you have the negative sign here, and the real loss function just to sum up these two terms, the feature matching term and the unsupervised term. And this is the whole architecture of it. Basically, the discriminator is just a multi-layer perception. It takes the intermediate representation, or you can say hidden representation from BERT. You have real data, then go through the BERT model encoder, text encoding. Basically, you can say there's a text encoder. Then you have the 768-dimensional hidden representation of that given example. Then feed it to the discriminator. Discriminator need to classify which class it belongs to. And also, discriminator takes the output from the generator as input. Generator also generates the fake hidden representation as they try to mimic the BERT hidden representation. the hidden representation generated by BERT. So discriminator will take these kind of two different types of input, but same shape of tensor, same shape of vector, then classify it. Is it real or is it fake? And if it's real, you need to classify which class it belongs to. So it's you can see this part, the BERT model and the discriminator, as a multi-layer perception on top of BERT. And in the inference time, they just completely discard the generator. So it just runs like a normal BERT, normal BERT plus one classification layer. So I say the generator takes the 100-dimensional vector, normalized from the value of the vector for each dimension is 0 to 1. And it's also, the generator is also just a multi-layer perceptron, and generated a 768-dimensional output, try to mimic the hidden representation generated by the BERT model. And I just have one question here actually. I feel a little bit concerning here. When you do the inference, you discarded the generator, right? Then what if your model, what if it's a real label data? Then your real example, then your model classified this as a fake class, K plus 1 class. How much will this affect the performance? But I guess it's not that much, because in their experiment results, they say they still outperform the standard BERT model by quite a significant margin. So it's not really a problem. Yeah, so just linger on unlabeled real examples a little bit. You may wonder, how do we calculate the loss for unlabeled real example? Because we don't really have label for that. So the discriminator will do one thing. It will predict if this example is real or fake. But when it predicts the unlabeled real example is a real one, then you also make a prediction which class it belongs to. Let's say the discriminator, say it's class number 1. But how can we calculate the loss? We don't have the label for that. So that's a little bit tricky for that. They don't actually calculate the loss when the unlabeled real examples is classified correctly. They only calculate the loss function when it misclassified as a fake class. The reason is simple, because we cannot calculate when it classified correctly. We don't have label for that. So as you can see in the unsupervised loss term, if the discriminator classify the real example, the real unlabeled example, as a fake one, then the loss function, they will be penalized. They will be penalized. So the loss function, the model wants to minimize these things from minimize the probability this happen. So you want to lower the probability of misclassifying the unlabeled real examples, and you only calculate in this part. Yeah, so let's look at the experiment results. They run the comparison on 6 different data sets. The first data set is 20 news group. They have news articles, and they have 20 different classes assigned to those articles. And as you can see, if you only train 1% of the data, then the model performance outperform the baseline BERT model by quite a lot. And this gap is only got smaller when you use 30% of the data. So you can see the data efficiency of the GAN BERT is extremely high. It's really, really high. And like this case, it's a question classification. You have the 2 categories. One is a coarse grain. You have fewer number of classes, more coarse grain classes, and you have fine grain classes. And you can see the similar result. Only when you train on the 1 or 2% of data, then the GAN BERT outperform the baseline BERT quite a lot. And in this coarse grain, the gap only got smaller when you use 20% of the data. But in this case, even when you use the 50% of the data, the GAN BERT still outperform the baseline BERT by quite a lot. And they suspect it's because of the fine-grained classification. When you have more classes, then the complexity of a task is even higher. So that's when the GAN BERT will be more beneficial from the GAN methodology. It's more just you can argue like when a task is more complex, you need a better model architecture to gain the better data efficiency. Definitely, when you fit infinity amount of data, this problem will be solved. But the reality is we always don't have that much data to train your model. So that's why we want to figure out what's the better way to structure our model so that it will be more data efficient. And they also run the comparisons on the sentiment classification task SST5, and similar trend when the data are very limited. The baseline BERT just underperform the GAN BERT. And one thing worth noting is they use how they obtain the unlabeled data. They basically when they use 1% of data, they use the rate of 99% of the unused data as unlabeled data. That's how they use that. But in the real world, it's easy to get the unlabeled data. We are not constrained in that given data set. And they also run this on the pairwise sentence classification. Is basically you have two sentences, sentence 1 and sentence 2, and you need to classify if these two sentences are maybe relevant or not, and etc. And you can see that on these three different tasks, the GAN BERT doesn't really have that strong advantage when you only use a very limited data, let's say 1%, 2%. But still, the advantage is still consistently outperform the baseline BERT model, even when you use more data, even when you use 10% of data. So the data efficiency still very superior. And the takeaways for today is the GAN BERT model is very data efficient. It does a very good job in the low resource setting. It's really good for industrial use cases because, like I always emphasize, we don't really have that many labeled data in the world. In this world, real world, most of data are unlabeled. Most of data sets are unlabeled. So if we can find a way to leverage those unlabeled data, we will have much better realistic performance. And also, the good thing of that is it doesn't have any additional costs in inference. It's good because even we have a word generator, but when we do the inference, we just discard that completely. Alright, congratulations. We have reached the end of today's video. And if you would like to receive more deep learning videos like this in the future, don't forget to subscribe. And other than that, have a nice day, and I will see you next time.